Okay, hi everyone again. Our speaker today is Chandrika Sadanand from Bowdoin College, and she's going to talk about hyperbolic cone surfaces and polygonal billiards.
Okay, thank you. All right, so this is joint work with Viveka, Erlandsson, and Chris Leininger, and Moon Duchen got the gang together, so thanks to Moon. An outline of the talk is as follows. So I'm going to tell you about a fun problem, and then we'll transform it into a second problem. And then we'll build some intuition for these problems, look at previous work on them, examples. Then we'll finally answer the problem, see some more examples, and then if there's time, talk about ideas in the proof. Okay, so here is the problem. So let's say that we have a polygon in the hyperbolic plane. So it looks, here's an example of a polygon in the hyperbolic plane. And let's imagine that this was a billiard table. So I have a billiard ball inside this polygon, and it moves. And when it hits an edge, it bounces off the edge like this, with angle of incidence equals angle of reflection. And it continues this way, bouncing around. Okay, so it hits C, then D, maybe, for example. Okay, each time with this angle of incidence equals angle of reflection, and it's moving along hyperbolic geodesics as it does this. And suppose on the side, somebody is recording the sequence of letters corresponding to the edges that it hits. So we get an infinite sequence of edges, infinite future and infinite past. And then imagine someone just, was hearing, let's say each letter corresponds to a note, E, C, D, So suppose someone is listening to this, this sequence. The question is, can they figure out the shape of the polygon? Of P, our polygon. Okay, so what I'm saying is for each billiard trajectory, I get a sequence, which I'm going to call this bounce sequence of letters.
This is a lecture that's been given at some Bowling Green State University.
A fun problem.
I hope they can't hear me.
Billiard trajectory.
Okay, and then let's look at the set of all the possible bounce sequences.
Hyperbolic plane.
Sounds like it might be interesting, but we'll see.
So it says Peter Scott at the top there.
That's me.
I think you're unmuted.
I'm zooming.
I think.
Oh, you're zooming.
But I'm muted. So
No, I think you're unmuted. But okay. Anyway, the question is, does the set of all possible bounce sequences B of P determine P? Okay. So first I want to show a little bit about how these two are related. So let's say we go to our polygon and we zoom in on one vertex like this. Okay, and I zoom in on one vertex. Here it is. It looks almost flat because I've zoomed in so much. Let's say this was side A, and let's say this is side B, for example. And if I shoot my billiard ball in towards this, into this corner, like this, let's say, notice that it's possible for it to bounce off A and B a few times before it leaves this corner. So I got A, then B, then A, then B, and then it left the corner. Whereas if I had a more obtuse angle, and I did a similar thing, sending the billiard ball in here, you can see that just after 1A and 1B, I'm getting sent away from the corner. So the more acute the angle is, the more I can get this AB, AB, AB back and forth type of subwords, alternating subwords. So here I just got A and B, and then I left the corner. So you notice that the smaller the angle, the longer the alternating subword that is possible. Okay, so we see that BP and P are related. Okay, so our main tool in studying this problem is something called an unfolding. So I'll explain what this is. Let's say that this here was our original polygon. Let's consider a slightly larger polygon made of 2 copies of the original. So here's the original again, and then now the second copy is a reflected copy of the original. So I put 2 copies of the original polygon together like this. And this makes a slightly larger billiard table around which a ball can bounce. And consider the map from here to here, where I simply fold the larger billiard table into the smaller one across this line. Okay, and what I notice here is that a billiard trajectory here will get folded up into a billiard trajectory here. So it's clear for a reflection like this that it's going to get sent to a reflection with angle of incidence equals angle of reflection over here. And it's clear that, bits of hyperbolic geodesic will get sent to bits of hyperbolic geodesic. So maybe you're worried about what's happening when a piece of the trajectory crosses the folding line. But because this angle equals this angle, then this angle will equal this angle. And so it will be this nice type of reflection that we're looking for. So we see that billiard trajectories, are sent to billiard trajectories. Okay. So now we've made a slightly bigger billiard table, but there's nothing special about that one edge. So why not do this over all the edges simultaneously? So instead of, we still have 2 copies of the billiard table. One is a reflection of the other. But now we attach all the corresponding edges to make a topological sphere. Okay, so it looks like this. And the folding map is now this. Okay, so from the 2 copies, we fold like this. And now here, if I just look at geodesics that avoid the cone points, so I'll call those non-singular geodesics. Those are going to be sent to the billiard trajectories here. So notice there's no more edges left here, so there's nothing to bounce off of. The geodesics are just going around, wrapping around and around and around forever here. Okay, so now this becomes a problem about geodesics on this surface. I would like a surface with non-positive curvature. So what I'll do is I'll take a branch covering of the surface and I branch over these points. Okay, and I just branch and branch until around each cone point, I have more than 2 pi total angle around. Okay, so now I have some picture like this, some surface of genus G, and it's tiled by copies of my original polygon, and neighboring copies differ by a reflection. And it has a hyperbolic metric, except it has all these cone points at the vertices of the polygonal tiles. Okay, and here again, the non-singular geodesics go to the non-singular geodesics in the previous level. Okay, so this is a finite sheeted branch covering over the vertices of our polygon. And we want it such that all the cone angles are greater than 2 pi. Okay, so this here, this is what I'm calling an unfolding. This is an unfolding of P. And the type of metric that it has, I will call hyperbolic cone metric. And so I'm calling the surface a hyperbolic cone surface. Okay. Let's go one step more, which is let's take the universal cover of U. So that looks sort of like the universal cover of a hyperbolic surface, except there are all these cone points. And I can't draw them all, but they're accumulating as I go to infinity. Oh, I have a question. Why do I exclude equal to 2 pi for the cone angles in the cover? I think it's better when it's more than 2 pi. For what comes later, you're able to sense where, from the metric alone, you can sense where all these polygonal tiles are meeting together. If you allowed 2 pi from the metric alone, you wouldn't be able to tell that. Okay, so here's this universal cover. And why don't we consider the endpoints at infinity? So there's this circle at infinity here. And let's consider pairs of endpoints at infinity. For a given pair, there is a geodesic between them. And if that geodesic does not hit any cone points, then it will get sent by this map to a non-singular geodesic here that wraps around in some way. Okay, so from these special, from these special pairs of endpoints at infinity, the endpoints such that a non-singular geodesic goes between them, I can get non-singular geodesics here, which go to non-singular geodesics here, which go to billiard trajectories here. So let me write down what that set is, these pairs of endpoints. So I'll say S1 for the circle at infinity, S1 infinity. I take the Cartesian product with itself, but I don't want to choose the same point twice. So I take away the diagonal. And I don't care what order the points show up in. So choosing X and Y is the same as choosing Y and X. Okay, so these are pairs of points at infinity. Okay, and a subset of this is, I'm going to call it GU, and it's going to be the pairs that bound non-singular geodesics. Okay, so this is the main tool, and we're going to come back to this setup again and again. You have your polygon, you double it to get this topological sphere. You take a finite sheeted branch cover, and then you take the universal cover, and then you look at pairs of points at infinity here that bound a non-singular geodesic. Okay, so now I'll show you how we use this tool. So suppose P1 and P2 are two polygons in the hyperbolic plane, and suppose that they have the same bounce spectra. They have equal bounce spectra. Okay, now let's make the following diagram. So here's P1 and P2. Right off the bat, we know that P1 and P2 have the same number of edges because that's the number of letters that show up in the bounce sequences. So if this one is a pentagon, then this one is a pentagon. Okay, and we want to think of P1 and P2 as the same topological space. You know, it has 5 vertices, 5 edges, 1 face, but there's 2 different metrics on it. There's the metric for P1 and the metric of P2. So here I'm thinking of this as identity map, but it's not an isometry. It's a deforming the metric from the P1 metric to the P2 metric. Okay, now let's take an unfolding of P1. So that means first we double P1, then we take a finite sheeted cover of that so that all the cone points are more than 2 pi. Okay. So I'm going to reveal more of the picture. Okay, here's the unfolding of P1. It's tiled by copies of P1. All right. Now let's take the double of P2, and we're going to find an unfolding of P2 that corresponds to this unfolding of P1. So the double of P1 and P2, if I remove the cone points, remove the vertices, these are both spheres with 5 points missing, or the number of points missing same as the number of vertices. So they're topologically the same. And the cover of that sphere with points missing that U1 corresponds to comes from a subgroup of the fundamental group of that sphere with points missing. Take the cover of the double of P2 corresponding to the same subgroup. That will be an unfolding of P2. Now, maybe some of the cone points don't have enough angle around them. If that is the case, we'll just take a higher cover. We'll unroll more around those cone points until we have 2 covers, one unfolding of P1, one unfolding of P2, so that they fold up in the same way. This folding and this folding happen combinatorially in the same way. And the way that U1 is tiled by copies of P1 is the same way that U2 is tiled by copies of P2. In fact, this deformation, we can just lift it up here and it will deform these tiles into these tiles and deform U1 into U2. We have another question. Do I know the cyclic order of the letters? Yes, yeah, I'm going to label it A, B, C, D like this in order around. Yes. Okay, so now we have these 2 unfoldings and we have this nice commuting diagram of maps. All right, and the goal is to promote this to an isometry. If I could make this an isometry, then I fold them up and I would get an isometry between these 2. This is what I would like to do. Okay. Let's look at the universal covers of U1 and U2 so that we can talk about those pairs of endpoints at infinity. Okay. So here I have the pairs, G1 is the pairs of endpoints at infinity here that bound a geodesic that doesn't go through the cone points, doesn't go through any cone point. Given one such pair here, so start with a pair in GU1. Given such a pair, that will give me this geodesic, which I can project down to a non-singular geodesic here. Okay, so that gives me a non-singular geodesic here. Now I fold up that non-singular geodesic and I get a billiard trajectory here. That has some bounce sequence. Because BP1 equals BP2, there must be a billiard trajectory here with the same bounce sequence. Okay. I don't know what it looks like, but it hits the equivalent edges in the same order. Now I can lift that here. And the way that I'm going to lift it is I'm going to see how this non-singular geodesic projected here. So I'll take one tile that non-singular geodesic runs through. And I see where that part of the billiard trajectory is sent. Okay, so let's say as it runs through this tile, suppose it went from side C to side A, just for example, okay? So I find the corresponding part of the billiard trajectory here that goes side C to side A, and there will be a corresponding part here going side C to side A here. And I'm going to lift this billiard trajectory to U2, starting on the corresponding tile and lifting that part that goes from C to A. And then I continue the lift. I continue to lift and I get some non-singular geodesic here. Okay. So that's the fifth thing I get. I've moved to this part of the diagram. I get a non-singular geodesic here. Now notice that this non-singular geodesic and this non-singular geodesic will pass through corresponding tiles and crossing corresponding edges of the tiling here and here. And because of that, we will have that geodesic goes through the same points at infinity here. So finally, I will get a pair of points in GU2 now. So I lift this non-singular geodesic here to a geodesic here. And I get a pair of points that's in a pair of points at infinity here that bounds a non-singular geodesic. So I get a pair in GU2. So what am I seeing here from this whole diagram chase? I see that if BP1 equals BP2, then GU1 equals GU2. Okay, so now the question is, given a surface S and a hyperbolic cone metric, let's call the metric phi, does G phi determine phi? Because if it did, then these two would actually secretly have the same metric, and then we would fold it down and show that P1 and P2 actually have the same metric. So this is the new question. Given a surface S and a hyperbolic cone metric phi, does G phi determine phi? This is the new question. Okay, so let's talk about previous work on questions like this. Okay, so I made a little table here. So all these questions are of the form, is this determined given this? So the first one is, suppose we had just a hyperbolic metric on a surface. And let's say, now bounce spectrum doesn't make any sense, but let's say that you were given the lengths of the closed geodesics and you knew which homotopy class those lengths corresponded to. That's what this marked part means. So suppose you were given the marked length spectrum. Can you figure out the hyperbolic metric? So the answer here is yes. And this is done by Otal. Okay, next question. Suppose you have a hyperbolic cone metric on a surface, and again, you're given the marked length spectrum. Oh, you don't see? Okay, oops. Hopefully now you can see. So the next question is, let's say you have a hyperbolic cone metric on a surface, and then you're given the marked length spectrum, same thing as before. Can you figure out the metric? So in this case, you can as well. And this is done by Hersansky and Paulin. Okay. Now, how about if you have a non-positively curved Euclidean cone metric? So that means it's a surface where most of the points have a neighborhood that's Euclidean, but then there's cone points and it's a non-positive curvature around those cone points. So it's angle more than 2 pi around those cone points. Suppose we had such a surface. And suppose we had, again, the lengths of all the closed curves and which homotopy classes those lengths corresponded to. Can you figure out the metric? So for this, it's also yes. So this is very encouraging, a lot of yeses. Okay. Oh, wait, oops. I think I'm getting mixed up. That's the wrong person. Okay. This was Bankovic and Leininger. Yes, okay. All right. So now these are the types of metrics that we're looking at in this talk, but now let's change this. Instead of the marked length spectrum, let's say that you had now these pairs of points at infinity that bound non-singular geodesics. And this we've kept the same now. It's still this non-positively curved Euclidean cone metric on a surface. So can you figure out the Euclidean cone metric given these pairs of points at infinity? So in this case, it's yes, except, except there's a small family of cases where you can't figure out the metric uniquely. And this is done by the same people as the work that I'm talking about today, Erlandsson, Leininger, and myself, as well as Moon Duchen. Oops, this is 2018. Okay. And then just the same way as what we talked about today with the unfoldings, in the same way, the answer to this problem will answer the bounce spectrum question for Euclidean polygons. So whether given the bounce spectrum, can you figure out the shape of the Euclidean polygon? So because this is yes, except, so is this yes, except. So this applies to the whole, to both of these rows. Okay, and so then finally we come to, for a hyperbolic cone metric, if you're given these pairs of points at infinity, and then if we had an answer yes to this, it would imply the hyperbolic polygon case. Yes, yes. Yeah, that's why I'm saying Euclidean. NPC is flat except for cone points. Yes. Yeah, non-positively curved Euclidean cone metrics. I hope that helps. Okay, so this is today's talk. Okay, so let's look at a special example, a special case. Here is the special case. So suppose you have a surface. Here it is with a hyperbolic cone metric. Let's call that phi1. All right. And suppose that it was possible to branch cover an orbifold. So suppose I could find an orbifold O1 so that this surface branch covers it. And I want the cone points to be sent to, to even order orbifold points. Suppose that I had this situation, okay, where I have this hyperbolic cone surface and it branch covers an orbifold, and all these cone points are sent to even order orbifold points here. Okay, suppose further that this orbifold has some non-trivial Teichmüller space. So suppose I can, without changing the topological type, deform this orbifold. So here I'm deforming the metric here to O2, but they have the same orbifold fundamental group. Then I could induce a deformation up here. And I would get a new surface of the same topological type as the original, but with a new metric, phi2. Okay, so let's consider this special situation. This isn't possible all the time, but suppose we had this special situation. Okay, well, in this case, let's look at the orbifold universal covers. So here they are. All right, and we can lift this map here. Okay, so this map, it deforms the metric, but its identity on the boundary. Okay, it's deforming on the inside. All right, and here we have pi1 O acting here. And I'm just going to put O because pi1 O1 and pi1 O2 are the same. They have the same orbifold fundamental group. Okay, so now suppose I had a geodesic here on my surface that goes through a cone point. Okay, so then because this branch cover sends the cone point to an even order cone point in O1, when I lift, so first I'll send this geodesic down to O1 and then I'll lift it here. So here it is, let's say. Okay. And it has to go through a point that there is an order 2 rotation around inside this group, because it goes to an even order orbifold point here. There has to be an order 2 rotation around this point by this action. So that means that there's an element in pi1 O that's going to swap these two endpoints because it's order 2 rotation. Okay, so what does that mean on this half of the picture? Okay, well, suppose that the corresponding geodesic here, suppose it missed all the cone points. Suppose it, I don't know where it went, but okay. Suppose it missed all the cone points here. Okay, so I lift it here. Whoops. I lift it here, and you know it's missing. It didn't go through any of the cone points here. Suppose that was the case. But this map acts by identity on the boundary, and it's equivariant with this orbifold fundamental group action. So there is an element here that swaps these two endpoints as well. Okay, so that means that when I apply that element, this geodesic has to get sent to itself, but the endpoints will get switched. So that geodesic has to get sent to itself with the endpoints at infinity switched. So that means there has to be a fixed point somewhere along this geodesic, and that will be an even order cone point in the quotient. So this is not possible that it avoids the cone point here. Every geodesic here that goes through a cone point, then the corresponding one will have to go through a cone point here in this special case. Does that make sense? Are there questions about this? So what we're seeing then in this case is that G phi1 equals G phi2. The pairs of points that bound non-singular geodesics for metric 1 is the same as for metric 2. But phi1 is not equal to phi2 because these don't have the same metric. We deformed the metric. So the answer to our question, does G phi determine phi, cannot be yes. At best, we can do a yes, except ... type of answer. Okay. So now let's share our results. So Erlandsson, Leininger, and myself. Okay, so the theorem is that this is the only exception. So that is if phi1 and phi2 are two hyperbolic cone metrics, on some surface S, G phi1 is equal to G phi2 if and only if phi1 equals phi2 up to isotopy, or our surface with the first metric can be deformed to our surface with the second metric, and that deformation is induced by an orbifold deformation, like in this example. So it's a lift of an orbifold deformation. Okay, and then this theorem implies for the billiard case if you have P1 and P2 hyperbolic polygons, both hyperbolic polygons, if the bounce spectra are equal, this is if and only if P1 and P2 are isometric, or, and now, oops. I mean, or there's some sort of deformation possible induced by an orbifold deformation. But to say that more concretely in terms of the polygons, it would mean the following thing. So, or there is a homeomorphism that goes from P1 to P2, but it preserves a tiling. So there's a tiling of P1, let's call it T1, and a tiling of P2, let's call it T2. Such that, or where adjacent tiles differ by a reflection. And also the angle of any tile meeting a vertex of Pi is of the form pi over 2k for some integer k. So what I mean by this is if this is your polygon, and then here's part of a tiling, these angles need to be of the form pi over 2k, the angles that meet the vertex of Pi. These angles do not have to be of that form, but these ones do. Okay, so let's look at an example so that we can see. Can I explain my counterexample again? Why don't I explain, because in my example, I'm going to show an example where there's some flexibility and then change it slightly so that it's rigid. So you'll be able to see the counterexample in the next example as well. So I hope it'll help, but if it doesn't, let me know and then I'll go back. Okay, so let's look at the following example. Okay, so let's make a quadrilateral in the hyperbolic plane such that all 4 side lengths are the same. Okay, and the longer that I choose the side lengths, the smaller the angle is. So I can choose the side lengths to be long enough, or the right length, so that the angles are of the form pi over n. Okay, and then now let me put, I see, I've already drawn some of it. Oops, okay. Well, let's put 3 of these together. Okay, so I'm gonna put 3 of these quadrilaterals together to form a larger polygon, a larger hyperbolic polygon. It's the hyperbolic version of this flat polygon, an L shape out of 3 squares. Okay, I chose the quadrilaterals so that their angle, this angle, this angle, this angle, this angle is all pi over n. All right. Okay, now let's consider the 2 cases, if n is even and if n is odd, and we're going to see 2 different stories happen. Okay, so if n is even, then it is possible to reflectively tile the whole hyperbolic plane with these squares. And so I get this whole little picture here, which hopefully I have drawn. Yeah, okay. So I can tile the whole hyperbolic plane with these squares, and then let me quotient by the orientation preserving subgroup of that reflective symmetries. Take the orientation preserving subgroup and quotient. And so I'll get this pillowcase here, this out of 2 copies of that square. Okay, and I can branch cover this orbifold with the double of my polygon. So here's my polygon down here, made out of the three squares, so-called squares. So here's the double, and I can branch cover the pillowcase so that all the cone points here are sent to these cone points here. And these cone points, what is the total angle around them? By the way, it's 2 pi over n, okay. And these are even order orbifold cone points. Okay, and now this orbifold, it has a non-trivial Teichmuller space. So it is possible to deform it. Like I could make a longer and longer pillow like this, you know, I can deform it. And that deformation, I can induce then a deformation of this double. And that deformation will not disturb the bounce spectrum. It will not disturb the set of geodesics that avoids the cone points. And so I'm going to get a whole family here. I'm going to get a whole family of polygons that all have the same bounce spectrum. So here's one that's coming from, you know, a more stretched out version of the pillowcase. I might get something like this, and this will have the same bounce spectrum, even though they don't have the same metric. Christopher Lloyd, is this satisfying to you, or would you like me to go back and explain the counterexample? Okay, great. All right, so now let's talk about, well, what if n is odd? So if n is odd, so let's notice what happened here. Here I was using the fact that I can tile my larger polygon by these smaller quadrilaterals. And these smaller, this tiling had all these properties that I listed here. Adjacent tiles differed by reflection, and the angles of any tile meeting a vertex of the polygon was of this form because n was even. But if n is odd, this is not the case. And so I would have to break it up further. So this tiling would not have all the properties I need. I would have to break it up further, perhaps something like this, you know? Okay, and then the quotient orbifold coming from the corresponding tiling would be some triangle orbifold. And that doesn't have any flexibility. I can't deform it like I could deform this one. And so because of that, this case is actually rigid. So you cannot deform the metric without disturbing the bounce spectrum in this case. So you can see that, you know, it's a delicate thing, but by and large, the situations where this can happen, whoops, I meant to circle this. The situations where this can happen are very rare. It's this special case where you can branch cover an orbifold and have all your cone points go to even order cone points. So for example, if your cone angles are, if the angles in your polygon are irrational multiples of pi, then you're probably in bad, you're out of luck. I don't think you can set this up in that case. You wouldn't be able to set it up. It would have to have rational angles. So this is a special case. So in most cases, the bounce spectrum will determine the shape of the polygon, but there's a few cases where you can't, and then this is what they look like. So this is a good stopping point. If you like, I can talk a bit more about the proof, but this is also a good stopping point. How long do you usually go?
We can go for 10 more minutes about the maybe sketch of proof.
Sketch of proof, okay. Okay, sounds good. All right, so let's sketch the proof of the first theorem. Where did I write the theorems? Oh, here we go. Let's sketch the proof of this one because it implies the other one. So let's suppose that we have a surface and we have two metrics on the surface and we have g phi1 equals g phi2. Okay. So in this case, because we don't know anything about the polygons, we don't at this point even know that we have the same number of cone points. In the case where we started with a polygon and then we made these unfoldings and stuff, because they were tiled in similar ways, they had the same number of cone points. But with this hypothesis, we don't even know that to begin. Oh, let me see, there's a question. In those special cases, does the bounce spectrum determine the cone angles? Yes, I think. Let me think about it. I'm a bit stuck. Yes, no. I have to think about it. I'm sorry. I don't want to say the wrong thing. I have to think about it. Okay, so the first step here is that we want to determine how many cone points there are in each metric. Okay, that's the first thing that we do. So here, I've written an outline of the proof. So the first thing that we want to do is get a bijection between cone points. And here we follow the ideas of Benkovich and Leininger. So they were the people that proved, they proved the similar problem for Mark length spectra and non-positively curved Euclidean cone metrics. Okay. So we follow their idea, and the idea is as follows. It's you look in the universal cover, and let's say this is with the first metric and this is with the second metric. And let's say you have a cone point here, and you would like to show that there's a corresponding cone point over here. That's what we would like to show. And what we do is we say, well, I can find a sequence of non-singular geodesics that converge to a singular geodesic that makes, angle pi on one side like this. I can approximate this geodesic with non-singular geodesics coming from the right-hand side. And I can approximate with non-singular geodesics this other singular geodesic that makes pi on the other side. So I have these two here, this one and this two. Okay. Now in this metric, it is not possible to, so I can have pairs of endpoints in G phi1 arbitrarily close to this and this, because I can approximate this geodesic with non-singular geodesics. And I can have points in G phi1 arbitrarily close to this and this, because I can approximate this pair with these non-singular geodesics. Okay, but there's no way for me to have this endpoint and any point in here in G phi1. This is not possible because the geodesic that goes between this and any point in here will have to pass through the cone point. And because G phi 1 equals G phi 2, the same betweenness properties are going on here. So there's this same triple where I can get as close as I like to this, to some geodesic going between these two, and as close as I like from this side to some geodesic going between these two. But somehow there's no non-singular geodesics in between, somehow. Well, the only way that that is possible, the only way that that is possible is if there's some cone point. So there has to be a corresponding cone point, it turns out. And so that's sort of the starting point, but we get a bijection between the cone points in the one metric and the other metric. Okay, from there, we sort of keep going and we keep leveraging these geodesics that make angle pi. So the next thing that we do is we show that if a geodesic, a non-singular let me draw this picture here again. The next thing that we show is if I take a non-singular geodesic here, it separates the cone points here into ones on the right and ones on the left. And this partition is preserved. So if I look at the non-singular geodesic between the same two endpoints in the phi 2 picture, it must separate the cone points. The cone points corresponding to these will be on the left. The cone points corresponding to these will be on the right. And so then once we have this preservation of partition, then we slowly promote this to preservation of triangulation. So we make a triangulation where the vertices of the triangulation are the cone points. Okay, and because of all this preservation of partition stuff and also the bijection of the cone points, there will have to be, for each one of these edges, we make an edge between the corresponding two cone points here. And there cannot be any surprise cone point that shows up inside a triangle here because of the preservation of partitions. Okay, so now we have a one skeleton and a map from between the one skeletons. And then the tricky part is to now get a map on the inside of the triangles. This is the whole tricky point. All right, and so how does that work? There's this complicated diagram. It's not so complicated, but okay, there's this diagram where what we do is, okay, we take our surface, we remove the cone points. This little symbol means remove the cone points, and then take the universal cover. And then surface with metric 2, remove the cone points, take the universal cover. And then this is the deformation between the two metrics, and this is the lift of that deformation. Okay, and the point of doing this, of removing the cone points and taking the universal cover, is that now we can develop onto the hyperbolic plane. Because before, our total cone angle might not have been a multiple of 2 pi, the cone angle at each cone point. And so we can't really develop onto the hyperbolic plane. But if we do this, now we can. So we develop onto the hyperbolic plane after that. And I didn't write it down, but actually one more thing, so let's call it 2.5 here. We show that if you have a forward asymptotic family in phi 1, that gets sent to a forward asymptotic family in phi 2. A locally forward asymptotic family. So something where there could be a cone point that causes them to diverge like this. But once I develop, they'll go to a forward asymptotic family here. And because we have the preservation of this forward asymptotic property, we actually get a map from the space at infinity here to the space at infinity here. We get a map from the space at infinity here to the space at infinity here. So if I had some family like this, that's locally forward asymptotic, maybe it got disrupted by a cone point. So these go off this way and these go off this way. But when I develop, they all get sent to a forward asymptotic family here in H2. And then the corresponding ones will get sent to a forward asymptotic family here. And so I get a map from the circle at infinity of this H2 to the circle at infinity of this H2. So that map I'm calling H. And then what we do is we show that in most cases, H has to be a Mobius transformation. So on the inside, actually, it has to be an isometry between these two. In most cases, that will be the situation. And then we pull that isometry back all the way down here. And so then this is an isometry. So the whole thing is to show this H, which is a map from the circle at infinity here to the circle at infinity here, is a Mobius transformation. I'm seeing it's 5:02 and I'm thinking I should probably stop. But thank you so much for your attention.
Well, thank you very much, Chandrika, for the great talk. Are there any questions for Chandrika?
I have a question. So what do you mean by GB1 equals GB2?
What do I mean by this? Let me go back to, this picture. Yeah. Okay. So let's say, do you remember this picture? So I was just deforming the metric between P1 and P2. And then I had the unfoldings of P1 and P2, that's U1 and U2. And then I lifted this deformation to a deformation between these two. So it's just, I have some tilings of U1 and then I changed the metric on each of the tiles and I get U2. Now I look at the universal cover of U1 and U2. So that's here. It's almost like the hyperbolic plane, but it has these cone points in it. And I lift the deformation again. So this is again identity, but not isometry. Okay. This will deform the inside, but it will actually be its identity on the boundary. I mean, it's identity map. Just the metric is changing. It's deforming the metric, but yeah, I'm not being clear. Let's see. Have to be. It's identity map. So it makes sense to talk about pairs of points on this boundary, and some of those pairs bound a non-singular geodesic according to metric 1, and some of them bound a non-singular geodesic according to metric 2. So it's the same, I'm considering it the same set of points at infinity. And then there's these two subsets, the pairs that bound a non-singular geodesic in metric 1 and the pairs that bound non-singular geodesic in metric 2. And sometimes
so
those
that's
subsets
where
are
I
equal.
got confused. You have this in the middle, you have this identity, not isometry.
Yeah, is it, how about here?
Okay.
Here it's the easiest.
So that's where I got confused. They are different objects. What do you mean identity map?
Okay, I mean that I consider, let's start here. And then we'll come to the other levels later. So here, let's start with, I have a topological space. It's a CW complex. It has 5 vertices, 5 edges, 1 face, no metric so far. Okay, and I consider the identity.
Okay, you are putting different metrics on the same space.
Yeah,
in that sense.
Yeah. That's right. And that's what's happening the whole way down. The difference between this one and this one is I remetrize all the tiles. The same way that these two metrics differ.
Yeah, then here you go to the boundary. It's very confused. Okay. Set-wise, you set-wise they're the same. Now the metric is different. Now the boundary, I don't see its identity.
Now, okay, so set-wise they're the same. Now let's consider some subsets of pairs of points at infinity. One subset is the pairs that bound non-singular geodesics according to metric one. Whenever I say geodesic, it has to be according to one metric or the other. So pairs of points that bound a non-singular geodesic according to metric one, pairs of points that bound non-singular geodesics according to metric two. These are two subsets of pairs of points at infinity. They could be equal, they could not be equal, they could, so.
Okay, maybe as Chris suggested, maybe this is quasi-isometric, which induces a homomorphism between the boundaries. And maybe what you mean GV1 equals GV2 is that 2 points in the first boundary, they are the boundary of non-singular geodesic, if and only if the two immediate points are the boundary of non-singular geodesic.
I see. I'm having trouble to both read and I'm so sorry. I should read what
what you meant is 2 points in the boundary of the first on the left. The bond on the left is in GV1.
Yeah.
If and only if the 2 points, the image of the 2 points is in GV2.
Oh, okay. Yeah, we don't have to think about it as identity and remetrizing. Okay. And then you could say it like that. Yeah. Okay.
Then I understand. Okay.
Okay, let's say that. Yeah.
Okay. Thank you.
Okay, any other questions or comments? Okay, then thank you very much, Chandrika. Again, it was a great talk. It was a pleasure really to listen to. Thank you.
Very nice talk. Thank you.